Hello everyone, I'm Eshwer, pursuing my BTech third year in the Department of ECE from MIT Andhra Pradesh. In this video, I will be dealing with Optimization Techniques course project on the topic so-called Traveling Salesman Problem using Exhaustive Search. Before we dive into the topic, let us see what is Exhaustive Search. Exhaustive search is the simplest of all search methods. In this method, the optimum of a function is found by calculating the function values at equally spaced points. Generally, this exhaustive search method is valid only for unimodal functions. Let us see the mathematical approach. In step 1, we'll be assuming a and b are lower bounds and upper bounds respectively, and we'll assume x1 is equals to a, x2 is equals to x1 plus del x, where del x is b minus a by n, and x3 is equal to x2 plus del x. In step 2, we will find f of x1, f of x2, and f of x3. If f of x1 is greater than or equal to f of x2 is less than or equal to f of x3, then the minimum lies between x1 and x3, and hence we'll terminate the function. Or we'll go to else condition. In else condition, x1 will be equal to x2, x2 will be equal to x3, and x3 is equal to x2 plus del x. In step 3, we'll see whether this x3 is less than or equal to upper bound. If yes, we'll go to step 2, and again we'll see whether this condition is satisfying or not. If this condition satisfies, the minimum lies between x1 and x3, and hence we'll terminate the function, or else we'll go to else condition. Let us see a small problem. Here I assume the function x square minus 4x plus 5 over the interval 0, 5. At first, we'll define the search space 0 and 5, and I define the step size as 0. 0.1, and we'll be evaluating from 0, 0. 0.1, 0. 0.2, and so on till 5. And we'll keep the track of each and every function value, and at last we'll return the minimum value. The minimum value for the above problem is 1, which is found at x is equal to 2. Let us see the Python code. In this Python code, this part returns the function value, and this exhaustive search minimum. Here initially it assumes x minimum is equal to a and function minimum is equal to f of a, and over this iteration in range a comma b, f of x is equal to x. If f of x is less than assumed minimum value, then we'll update the f minimum as f of fx and x minimum as x, and at last we'll return the function minimum and as well as x minimum, and we'll print the value. Let us see the output for this code. The output for this code is x minimum is 2 and f minimum is 1. Let us see the applications of exhaustive search method. Some of the applications are cryptography, global optimization, combinatorial optimization. In this video, I'll be dealing with combinatorial optimization. What is combinatorial optimization? Combinatorial optimization deals with finding the best solution from a finite set of possible solutions. The example to the combinatorial optimization is traveling salesman problem. The objective of the traveling salesman problem is to find the shortest possible route that visits each city exactly once and returns to the starting city. The exhaustive search remains an important benchmark for TSP algorithms and provides a baseline against which the other algorithms can be compared. Let us see the traveling salesman problem. In traveling salesman problem, we will be given a set of n cities and the distance between each pair of the cities. This TSP involves finding the shortest possible distance that starts and ends at a particular city. The TSP has numerous real-world applications such as logistics, transportation planning, and in circuit design. Let us see the steps for solving traveling salesman problem. Initially, we assume city1 as starting and ending point. Now we'll be having n-1 factorial possible combinations, and we'll be keep tracking each route distance, and at last we'll return the route with minimum distance. Let us see the example. Here the A, B, C, and D are four cities given. So there will be n-1, which is 4 minus 1 factorial, which is 6 possible combinations are there. I have written each possible tour, 6 possible tours in this tabular format, and I return the minimum distance of each possible tour. After finding it, the route 1 and route 6 will be having the minimum distance. Let us see the following code. Let us see the following code in VS Code. This is the code for finding the shortest distance to the above problem mentioned here. Initially, I assumed 0, 1, 2, 3 as A, B, C, D cities. Uh, the distances from 0 to 0 is given as 0, 0 to 1 is given as 2, 0 to 2 is given as 8, and 0 to 3 is given as 5. And I have given and I have initialized each and every distance from a particular city. And in this code, I will be finding the shortest path and as well as shortest distance. Let us run the code. The shortest path is 0, 1, 2, 3, and returning to the same city 0. The shortest distance covered is 17, which we have already seen in this above problem. Now let us see the generalized Python code. In generalized Python code, I assumed cities as coordinate access points. Here x comma y defines the city, and here we'll be finding the distance between two cities using the formula square root of y2 minus y1 whole square plus x2 minus x1 whole square. This defines the tour distance, and this defines the possible tours. Let us see the code in VS Code. Let us see a small problem to the above example. I initially assumed 0, comma 0 as city A, 1, comma 1 as city B, 2, comma 2 as city C, 3, comma 3 as city D, and 4, comma 4 as city E. The distance between the cities can be calculated using the formula square root of y2 minus y1 whole square plus x2 minus x1 whole square, and the two distance can be calculated from this function. And at last, I'll be printing the minimum tour and as well as minimum distance. Let us run the following program. The minimum tour is I initially assumed 0, comma 0 as city A, 1, comma 1 as B, 2, comma 2 as C, 4, comma 4 as E, and 3, comma 3 as D. The minimum distance uh, covered is 11.313. Let us see the generalized Python code. Here I defined cities in the form of coordinate access points. The distance is calculated using the formula square root of y2 minus y1 whole square plus x2 minus x1 whole square. And this part of the code defines the total distance of the tour. And this part of the code defines the number of possible tours. And in this, we'll compute all permutations. And at last, we'll find the tour with minimum distance. And after that, we'll be printing the minimum tour as well as the minimum distance. Let us run the following code. The minimum tour for the above code is 5, 1, 4, 3, 2, 0, and again I will be going to city 5. The minimum distance covered is 21.09. Let us see the 2D graphical representation of the previous example. We should import matplotlib.pyplot library to plot the following graph. Here I initialize the coordinate access points from the previous example. I initialize the following order of the cities in the tour, and we are initially we are assuming each city with color blue, and this part of the code defines the tour with arrow directions, and this part of the code defines the last arrow from the last city to the starting city. Using plt.plot, we are plotting the graph. Here I assume the starting point with a red color. Let us run the following code. This is the minimum tour graph starting from this point and ending at this point. Let us see the conclusion for this traveling salesman problem using exhaustive search. Exhaustive search guarantees finding optimal solution for traveling salesman problem, and the time complexity of the algorithm is O of n factorial, which is very very large. And exhaustive search is only practical for very small instances of the traveling salesman problem. Here, these are the following references I have gone through for preparing my presentation. And thank you all for patiently listening to the video.